Hello, everyone. Welcome. Hi, I'm Oliver.
Hi, I'm Lily.
You are listening to Science in Easy English. Could a solar storm destroy civilization?
That is quite the question for our deep dive today.
It really is. I mean, you spend your entire life surrounded by technology, right? You just treat it like it's solid rock.
Oh, absolutely. We take it completely for granted.
Yeah, exactly. But looking at the stack of space weather data you brought in today, we've got NASA satellite readouts, historical chronicles, a Google-backed submarine cable study, even a FEMA tabletop exercise. You start to realize our entire digital world is actually built on this really fragile magnetic fault line.
Yeah, and the tension on that fault line is building as we speak because, well, we're currently right in the peak of solar cycle 25.
Which is the sun's natural 11-year activity cycle. Right.
Exactly. And if you've spent any time online lately, you've probably seen those viral articles screaming about an impending internet apocalypse.
Oh, yeah, my feed is full of them. Total doom scrolling.
Right. So our mission today is to cut through that noise. Separate the actual science from the social media fear-mongering and explain what the real threat actually looks like.
Okay, let's unpack this. Because to grasp the threat, we have to look at the engine driving it. And your notes dive straight into the mechanics of something called differential rotation.
Yeah, differential rotation.
Hmm.
It sounds complicated, but it's just because the sun isn't solid. It's a massive ball of superheated plasma, so its equator actually rotates faster than its poles do.
Which is wild to think about.
It is. And that differential rotation is literally the engine of space weather. Imagine the sun's magnetic field lines running straight from north to south.
Okay, got it. Like a giant bar magnet.
Right. But as the equator spins faster, it drags those invisible lines along with it. Over months and years, they get stretched, they get twisted, and incredibly tangled up.
Your research notes brought up a brilliant analogy for this. Think of a toy airplane, right? The
Ah.
kind with a rubber band attached to the propeller.
Oh, that's such a good way to visualize it.
Yeah. When you wind that propeller, the rubber band gets tighter, it twists into knots, and it's just storing up all this potential energy. Eventually, it hits a breaking point and snaps.
Exactly. And on the sun, when those twisted magnetic fields finally snap and realign, they release a mind-boggling amount of energy.
Which leads to the eruptions.
Right, the two primary types of solar eruptions. First, you have the solar flare. This is essentially a massive flash of electromagnetic radiation, mostly like light and X-rays.
And because it's just radiation, it travels super fast, right?
Yeah, at the speed of light. So it hits Earth in about 8 minutes. It ionizes our upper atmosphere and causes high-frequency radio blackouts.
So a flare is powerful, but it's not the main event for infrastructure on the ground. Like, if a solar flare is the flash of a cannon firing, the coronal mass ejection, the CME, is the actual cannonball.
What's fascinating here is how accurate that analogy is. A CME isn't just energy or light, it's physical matter.
Wow.
Yeah, it's a massive cloud of superheated magnetized plasma, sometimes containing 1 billion tons of solar material.
1 billion tons? That is hard to even wrap my head around.
I know, it's huge. And because it actually has mass, it travels much slower than a flare. It takes anywhere from 15 to 72 hours to cross the 93 million miles of space and hit Earth.
Wait, if a CME is actual physical matter with mass, it's going to hit our magnetic field like a kinetic weapon.
Yeah, it really does.
That sounds far more destructive to a physical power grid than just a burst of X-rays messing with radio signals.
It is far more destructive. And Earth has taken direct hits from these CME cannonballs before. The historical record you've got in front of you reads almost like science fiction.
Oh, totally. The benchmark one is the 1859 Carrington event, right?
Yes, the Carrington event.
Yeah.
The CME was so intense it pushed the auroras, which you usually only see at the poles, all the way down to Colombia.
That's insane.
I-
And there was that bit about the gold miners in the Rocky Mountains.
Oh, yeah, they woke up in the middle of the night, thought it was morning because the sky was so incredibly bright, and just started making breakfast.
The visual of that is stunning, but the technological impact is what really caught my eye. Because in 1859, the absolute peak of technology was the telegraph.
Right, the cutting edge of the Victorian era.
And the storm basically overloaded those telegraph wires with geomagnetically induced currents. We're talking wires catching fire, operators getting shocked.
Yeah, it's chaotic.
And in some cases, the operators actually disconnected the batteries, and the telegraphs just kept sending messages, powered entirely by the ambient electrical current from the solar storm.
That's how much energy was just hanging in the air.
I mean, has a direct hit like that actually happened since, or is this just some weird 19th century anomaly?
No, it has absolutely happened since. And as our technology evolved, our vulnerability actually deepened.
How so?
Well, take August 1972. A solar storm caused dozens of sea mines off the coast of Vietnam to spontaneously detonate all at once.
Wait, what? How does a storm in space trigger a mine underwater?
So those specific sea mines were designed with magnetic triggers. They were supposed to detonate when the massive steel hull of a ship passed over them, which alters the local magnetic field.
Ah, oh,
But the CME caused such a violent, rapid fluctuation in Earth's overall magnetic field that the analog sensors in the mines registered it as a massive ship overhead. Boom!
that is wild. The storm essentially tricked the analog sensors into firing.
Precisely. And then, jumping ahead to March 1989, we saw the Quebec blackout.
Right, I've heard of that one.
Yeah, a geomagnetic storm induced massive currents into the Hydro-Quebec power grid. The excess current completely saturated the magnetic cores of their transformers.
And transformers are crucial for the grid.
Completely crucial.
Yeah.
Within minutes, the system collapsed, leaving 6 million people in the dark and cold for 9 hours.
And these transformers, they aren't just popping a fuse, right? They literally melt under that kind of saturation.
Right. The geomagnetically induced current causes the transformer core to heat up catastrophically. It can melt the copper wiring and destroy the unit entirely. And even more recently, just in May 2024, the Gannon storm disrupted precision GPS for farmers.
Oh, because modern agriculture uses GPS for planting.
Exactly. They rely on tractors that navigate with inch-level accuracy to plant seeds. But the ionized atmosphere refracted the GPS signal so badly that tractors were off by up to 10 feet.
10 feet, that ruins the entire crop line.
Yeah, it forced farmers all across the Midwest to just halt their operations completely.
And then your notes included these things called Miyake events.
Oh, the tree rings. Yeah.
Scientists looking at ancient tree rings found massive, totally unexplained spikes in carbon-14 dating back to the year 774 AD. And carbon-14 comes from cosmic rays hitting the atmosphere, right?
Right. So a massive spike means a solar particle event that was orders of magnitude stronger than even the Carrington event.
It's just a really sobering reality check. Like, the sun has gears we haven't even seen it use in modern recorded history.
It really is.
I mean, if a solar storm could make a 19th century telegraph run without a battery and catch fire, what on earth would a Carrington or like a Miyake event do to our modern, hyper-connected digital grid today?
And that exact question is the focus of the study you shared by Sangeetha Abdujyothi. She's an assistant professor at UC Irvine, and her work is backed by VMware Research.
Okay, what did she look into?
She specifically analyzed the ultimate vulnerability of our present day: submarine internet cables.
The ones that sit at the bottom of the ocean.
Exactly. They sit at the bottom of the ocean and carry virtually all international internet traffic.
No, wait a second. The fiber optic cables themselves are just transferring light through glass, right?
Yes.
And glass isn't magnetic, so shouldn't the data itself be immune to electromagnetic interference from a solar storm?
You're totally right. The fiber optics are immune, but light degrades over really long distances.
Oh, sure. It fades out.
Right. So to fix this, the cables are equipped with devices called repeaters. They're placed every 100 to 150 kilometers to boost the optical signal so it actually makes it all the way across the ocean.
Okay, and I'm guessing those repeaters need power.
Exactly. They need electricity.
Mm.
So alongside the glass fibers, there is a highly conductive copper cable running the entire length of the ocean floor just to power those repeaters.
Ah. And copper running thousands of miles across the ocean floor is essentially a giant underwater antenna.
Exactly. According to Faraday's law of electromagnetic induction, a massive fluctuation in Earth's magnetic field induces electric currents in long conductive materials.
So a transatlantic submarine cable just absorbs all those geomagnetically induced currents.
Yes, and if that huge surge of electricity fries even one single repeater, the entire cable goes down. The signal simply cannot make it across the ocean.
And if multiple cables go down, the economic stakes are just staggering. Like looking at the numbers in the research, in a global internet outage, Amazon stands to lose over $44 million per hour.
Per hour, it's unreal.
Alphabet could lose $20 million per hour. On a national scale, the U.S. economy could bleed over $303 million every single hour the internet is down.
The financial bleed would be absolutely catastrophic.
Mm.
But if we connect this to the bigger picture, we have to look closely at the probabilities, right?
Right.
Sangeetha Abdujyothi's study estimates the actual chance of an extended global internet disruption occurring in the next decade is somewhere between 1.6% and 12%.
So is this where the line between actual science and social media panic kind of gets blurred?
Yeah, I'd say so.
Because losing the internet sounds like a blockbuster sci-fi movie, the whole internet apocalypse thing. But the
Mhm.
math says a total months-long outage is actually a pretty rare worst-case scenario.
Misinformation thrives on those worst-case scenarios. A total internet apocalypse is highly unlikely. However, we really shouldn't let the exaggeration blind us to the compounding risks.
What do you mean by compounding risks?
Well, even if the global internet doesn't permanently collapse, localized grid failures, aviation disruptions, and severe damage to our PNT systems are highly probable.
PNT.
It stands for Position, Navigation, and Timing. That's our GPS, our military communications, and the time stamping for global financial transactions.
Oh, wow. So if the timing is off, the financial system's just halt.
Exactly. The cascading friction of those specific failures would be globally disruptive, even without losing the entire internet.
Which brings us to a massive dilemma. If the financial and infrastructural stakes are in the trillions of dollars and the cascading failures are that disruptive, why can't we just forecast these storms the way we forecast a hurricane?
I wish we could.
Like, why aren't we just boarding up the digital windows, so to speak, a few days in advance?
Because space weather prediction is currently about 50 years behind terrestrial weather forecasting.
50 years.
Yeah, we simply lack the sensor density in space. To understand how critical this gap really is, look at the recent tabletop exercise conducted by FEMA and the Johns Hopkins Applied Physics Laboratory.
Right. They gathered emergency managers to simulate a response to an incoming massive CME.
Yes, and this is where the blind spot comes in.
This part absolutely blew my mind because we can see the CME erupt on the sun, right?
Yeah.
We know the cannonball is in the air, and we can track it for the 15 to 72 hours it takes to cross space.
We can see it coming the whole time.
So why were the emergency managers in the FEMA exercise panicking?
Because the severity of a CME's impact on Earth depends entirely on its magnetic orientation, and we cannot see that from afar.
Oh, I see.
Think of it like holding two bar magnets. The CME has its own magnetic field, and Earth has its magnetic field. If the CME's magnetic poles align with Earth's, meaning north to north, they mostly repel each other.
Kind of like pushing two positive sides of a magnet together.
Exactly. The cloud basically bounces off our magnetosphere and we get some spectacular auroras, but the grid stays largely intact.
But if the poles are opposite, like if the CME's south pole hits Earth's north pole, they magnetically connect.
Yes, they undergo magnetic reconnection.
They collide in this massive energy exchange that rips open Earth's protective bubble and dumps all that radiation and electrical current straight into our upper atmosphere, right down into the grid.
Yes, and the terrifying blind spot here is that we cannot measure the magnetic orientation of that incoming plasma cloud until it physically washes over our early warning satellites.
And where are those satellites?
They sit at the L1 Lagrange point.
Okay, the L1 point is a gravitationally stable spot about 1,000,000 miles away, right? Sitting directly between Earth and the sun. 1,000,000 miles sounds like a really comfortable buffer.
It does sound like a lot, until you remember a CME is traveling at millions of miles per hour.
Oh, right.
Yeah, So by the time the cloud hits that L1 satellite and the satellite beams the telemetry back to Earth, telling us if the magnets are aligned or opposite, we only have about 15 to 60 minutes before the storm actually hits our atmosphere.
So it's literally like watching a hurricane approach the coast for 3 days, but you have absolutely no idea if it's a mild rainstorm or a Category 5 monster until it is exactly 30 minutes away from your house.
It's exact.
That is an impossible situation for an emergency manager.
It really is. This raises such an important question. How do you manage global emergency protocols with only a half-hour warning?
Hmm.
For the FEMA participants, it was an absolute nightmare.
I can imagine.
Do you proactively shut down entire regional power grids just in case? Doing that causes massive economic damage, it cuts power to hospitals, and creates total chaos for a storm that might just bounce right off.
But if you risk leaving the grid on and those massive high-voltage transformers get saturated and melt down, you can't just run to the hardware store for a replacement.
No, you definitely can't.
Those giant transformers are custom built. They can take months or even years to manufacture. If they melt down, millions of people are stuck in the dark indefinitely.
The friction between calling a false alarm and risking a catastrophic failure is just agonizing for these officials.
So given that anxiety-inducing 30-minute warning window, what is humanity actually doing to defend itself?
Fortunately, the sources point out that humanity is taking active steps to widen that warning window. NASA and NOAA are spearheading something called the Space Weather Next program.
Oh, that's good news.
Yeah? They are launching a new observatory called Solar One. But more importantly, they are collaborating with the European Space Agency on a mission called Vigil.
Vigil is heading to the L5 Lagrange point, right? Now, L5 isn't sitting directly between us and the sun. It's located 60 degrees behind Earth in its orbit.
Right. So imagine Earth and the sun on a clock face.
Mm.
If the sun is in the center and Earth is at 6 o'clock, L5 is over at 4 o'clock.
Okay.
By parking a satellite there, we get a side-angle view of the space between the sun and Earth.
Oh, that's clever. It's like putting a camera on the shoulder of the highway instead of just staring straight into the headlights of oncoming traffic.
That's a great way to put it. We'll be able to look at the CME structurally from the side as it travels.
Which gives us earlier warnings.
Exactly. It gives us earlier warnings about its speed, its density, and potentially its magnetic structure before it ever reaches the L1 point.
That sounds like a total game changer for forecasting.
It really is. And, while we spend so much time focusing on the destructive power of space weather, your sources actually highlighted a fascinating counterintuitive benefit.
Oh.
The sun's violent activity actually provides a crucial buffer for Earth.
Right, the cosmic rays.
Yeah.
The entire solar system is constantly bombarded by galactic cosmic rays, like insanely high energy radiation from supernovas and black holes deep in interstellar space.
And that background radiation is actually far more dangerous to human DNA and space hardware than standard solar radiation is.
Which is wild. So when the sun is highly active, like having these magnetic temper tantrums and blowing out CMEs, its overall magnetic field swells up.
Right. It pushes back against interstellar space, creating this massive buffer that shields Earth from those deadly galactic cosmic rays.
So heightened solar activity is actually the safest time for astronauts to travel into deep space regarding background radiation.
Yep. Even though the local risk of a CME hitting them is higher, the overall background radiation drops.
It's a cosmic trade-off.
It really is.
But looking at the extreme end of that trade-off, like those ancient 774 AD Miyake events we talked about, that brings up one of the most mind-bending theories in the research.
Oh, the Fermi paradox connection.
Yes. The Fermi paradox asks, if the universe is so vast and so old, where are all the aliens? Why haven't we seen any signs of advanced civilizations?
And one proposed solution to the paradox is the concept of a great filter.
Right, an evolutionary or cosmic hurdle that almost no civilization manages to survive. And some astrophysicists suggest that extreme stellar activity could be that great filter. Here's where it gets really interesting. You're saying the very star that gives an alien civilization life might be the ultimate speed bump for their technological evolution across the universe.
Think about it. Our sun is a relatively calm, middle-aged yellow dwarf,
Right.
yet it can still unleash Miyake events capable of frying unprotected global electronics. Many other stars out there are far more volatile, throwing off super flares regularly. Imagine a civilization reaching our level of technology. They invent telegraphs, then power grids, then a global internet.
Yeah.
But every few hundred years, their star routinely blasts them with a super flare that completely resets their technological progress.
So they rebuild, they advance again, and boom, they are pushed back to the dark ages. The infrastructure is melted again.
Exactly. Perhaps the reason we don't see a universe teeming with hyper-advanced starfaring civilizations is that the natural space weather of their home stars keeps them permanently trapped in this cycle of destruction and rebuilding.
That is a heavy, humbling thought. We are literally at the mercy of the cosmos, spinning on a rock, hoping the magnetic poles of the next plasma cloud happen to point the right way.
We really are.
So what does this all mean for us? We've gone on quite a journey today.
We have.
We started with the twisted magnetic rubber bands on the surface of the sun, snapping into flares and massive CME cannonballs. We looked at the flaming telegraph wires of the 1859 Carrington event, how magnetic fluctuations tricked analog sea mines into detonating, and those ancient warning signs hidden in tree rings.
We also explored the very real vulnerabilities of our modern era. Those fragile repeaters on submarine cables sitting at the bottom of the ocean.
Right.
And the fact that a direct hit with the wrong magnetic orientation could cost the global economy billions of dollars an hour, paralyzing our critical PNT infrastructure.
And we cover the terrifying reality that right now our warning system only gives emergency managers about 30 agonizing minutes to decide whether to plunge millions into darkness or risk melting the grid.
It's a tough spot to be in.
Every single time you use your GPS to navigate, every time you stream a movie, or honestly, every time you just flip on a light switch, you are relying on a fragile web of technology that is fundamentally at the mercy of a 4.6 billion-year-old star.
It completely reframes how you look at the daytime sky. Earlier, you talked about how we build our civilization assuming the foundation is solid rock, when it's really a fragile magnetic fault line.
Which leaves you with one final thought to mull over. As we push toward this bold new era of artificial intelligence, quantum computing, and an entirely automated, hyper-connected global grid, are we simply building a taller lightning rod?
Wow.
Could our relentless drive to automate and connect absolutely everything actually be making us more fragile to the natural rhythms of the cosmos? Something to think about the next time your internet drops out. Thanks for joining us on this deep dive. Keep asking questions and keep looking up. See you next time.